we're going to go back through this very quickly. A quick review for those of you who are new to the game, and just to kind of reset the context before we get into our next sections here. So, everybody, notebooks out. Class has begun. So, data structures and algorithms, basic structure. So, at the highest level, let's talk about what a data structure is. So, very quick reminiscent of a handful of things that we were able to list off last time. A variable is a data structure, right? Anything that holds data is a data structure. Arrays, lists, dictionaries, or hash maps, whatever you call them, graphs, trees, stacks, and queues. If it's got data in it, it's a data structure. The reason we have different structures is to optimize different things, such as the most two common examples are speed of how quickly can I answer a certain question, and that question will change, such as how big is this, or is this item in the structure, stuff like that. And size. How little space can we use to store this is often a concept. Objects too. I'm going to leave this just because these are our last notes, but yeah. So we went over arrays briefly. Arrays are defined at a fixed size. The moment that you initialize an array, you know how many spaces it will take up, and it literally blocks out that memory for you. All the memory blocks are the same size in most languages. In any language where they're not, it's not really an array, it's just lying to you. Or it's doing an array of objects, blah, blah. So again, assuming that we're using some strongly typed languages here, any object can be held in an array, the size is always predetermined, and you can't change the size. Any language that tells you you can is lying and just giving you a new array later and copying everything in. Each element is the same size, or it's hiding it internally as some other type that's the same size, and the key is the literal memory stamp is fixed. So this is memory. This is exactly how much space the array will take up. Cool? Cool. Keep in mind, this is review, so I'm just covering these super quickly, not really going through all of this at a high level. Right? So when you look at an array, if you wanted to ask the question of how many items are in here, the only way to really answer that is to iterate through. Again, don't worry about having size and everything. At the end of the day, if I just gave you the structure and no other info, you'd have to go one by one and count, right? And if I asked you, is 12 in the array, you would either have to iterate through and search, or do a binary search if you're familiar with that algorithm. Now, all of those things seem really obvious and really straightforward and not particularly necessary, but then you come into the linked list, or just the regular list. Did I skip? No. Trying to keep as much on screen as we can. So now here we're talking about nodes. Each node has data and another node that it points to, right? And so that's the basic object type of the node. It has a value and a next. And so the key here is that you kind of comprise this list by chaining these pointers, chaining the nodes together, right? So the idea here is the difference of a linked list versus an array is this list is infinite. Right? I could just keep linking more and more and more, so there's no defined size here of the total thing. And you could really use any object if you wanted to. But at the end of the day, each element is probably the same size, and each element is stored in a node containing that data. So I assume most of the time that we're going to be dealing with the same data type just for consistency, but there's a big difference in how that memory is stored. Right? That memory is stored in individual chunks. So as opposed to our array, where there's one giant brick of memory, where computers are built to literally iterate step, 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 making arrays really fast, linked lists end up being pretty slow, relatively, because you have to jump in memory to wherever this stuff is stored, because it can be anywhere. Cool. Now, operations on a linked list, there's a handful of them: adding an element, deleting an element, inserting an element. So, to start, we talked about adding an element. First thing you do is create a new node, and then you add it somewhere. So we talked about prepend, append, and insert. If you want to put it at the beginning, we assume that the linked list has a head and a tail object, right? So your linked list is literally this object that has the first node and the last node. So if you want to add it to the beginning, you basically just toss it over here, link it to this guy, and then change the head, as we have here. If you want to add it to the end, you go down to the tail, right? You set this one's next to whatever this new node is. I don't actually want to move stuff here. And then you update that tail value, right? And it keeps tracking. And again, this is just review very quickly. So don't worry too much if you don't get this. Go watch the other VOD. This is just because we'll need to reference these. And adding at an index is the most complicated of all of them, which is basically you just iterate through until you find where you want to insert between. So say I want 50 to be right here. I keep track of this guy, and basically I have this one point up to 50, and 50 point back to 6. Then we talked about stacks and queues. So the difference between stacks and queues is the legendary statement of LIFO and FIFO, or last in, first out, first in, first out. You can think of a stack as a can of Pringles. They put the Pringles in one at a time. The last Pringle they put in is the first Pringle you eat. You cannot eat a Pringle from the bottom of the can. That is physically impossible. Don't challenge me on that. And when you think of a queue, you can think of it like a grocery store. First person that gets online is the first person that gets out of line, right? If you're first, you get checked out first. Easy enough. And we just did some basic add and remove, adding and popping, which is the term for removing and removing a value and returning the value. Yeah, what's up, Gila? Yeah, for sure. Dynamically allocated memory is a huge benefit in certain contexts. So what we talked about, the big difference here, is that no matter how you put in and pull out things in a queue, the order that you add them is always the order they will come out, even if you pop in the middle, because it goes from the first thing you went in. But with stacks, that's not always true. So with stacks, you can add a few and then pop, and it will actually affect your output order here. Simple, straightforward. And this is our output order here. I'll pop back up because this is kind of important. With an array, if you know you'll need this much memory and you're going to allocate it anyway, it can be a benefit to allocate it ahead of time because this storage will give you speed, which sometimes is something that you really care about. Like we said earlier, it's all about what your priorities are, right? But if you don't care about the speed as much, and this is like you'd have to care about it at a very low level and you're willing to chunk that memory out early, then you'll get the speed benefit. If not, then this is much more lightweight and requires much less because you only allocate what you need as you need it. So again, depends on how much you know. A lot of data structures act on just how much information you have. So it's like with a stack and a queue, you don't actually know what's going to come into them, but you do know that whoever gets into this line first needs to be let out first, and whoever gets into this stack last needs to get let out first, right? Pringles can, grocery store. Simple. Now we talked about how we can take that structure of the linked list and turn it into a stack or a queue. So doing nothing to a linked list, but keeping our head and tail tracker, so 1 being the head, 7 being the tail, if you wanted to implement pop on this linked list, all you would have to do is remove the last thing that we put on, which would be the tail. So you remove the tail and return 7, which is at the top of our stack, and then you set the new tail. So you'd set the tail to 6, right? Now if you go into a queue instead, and you wanted to pop, you would pop the first thing that you added to this list, which again, assuming you've been adding on to the end, is the head. So you would simply chop the head off and set a new head, which is something that we'll find again later when we get to heaps. But that's literally it. With these simple, effectively 2-line functions, quote unquote, conceptually 2 lines, you're able to take a linked list and turn it into 2 other data structures like that. Super cool. Now, finally, we started talking about trees. Now, I defined trees very loosely last time because we didn't have the context of graphs. But the key is, with a tree, is effectively, without getting too into like very, very, very specific categorical definitions here, each node has a piece of data and a number of children. And whatever the kind of tree is, you generally have the same number of children, but you don't have to. So in this case, the top is the root, and so the root has no parent, it's an orphan, and the leaves of the tree, it's an upside down tree because programming, are any nodes that don't have children, right? So 2 is not a leaf because it has 3 as a child, but 3, 4, and 4 all do not have leaves. Now this is just a generic tree. So the key here is it's a concept of parents and children, right? There is this sort of hierarchy. We see that in trees, we won't see that in graphs, so be prepared. Yes, the trees are upside down because they are Australian trees, was the joke last time, which is still so great. So this is super generic, and remember that this relationship is one way. It only goes down. Straight down, straight down, straight down, right? And it can't go back up. The arrows only go one way. It doesn't seem too important. It seems kind of obvious now. It will matter later. So remember that fact. Now we talked about binary trees in particular. The only difference between a binary tree and any other tree is that a binary tree is a tree where each node has at most 2 children. And conventionally, instead of just having a list here, since we only have 2, we'll just have the left child and the right child. So in this case, this is our leaf, this is our leaf, and this is our root, right? And you can kind of see how we have the data split here. So for the root in particular, you can see that it has 2 children in this case, but any leaf, whatever the data is, will have no children, right? And any regular node will look something like this, where it just has the data, and maybe 1 child, maybe 2, who knows? Depends. But this is a binary tree, BT. And we haven't gotten specific yet. We haven't added any rules yet. These are just terms to be familiar with, because sometimes you'll get some wacky questions that are a little more specific, and we'll give you a ternary tree that has 3 types, or an n-ary tree where they kind of don't care how many are in there. But the most common tree you'll ever see is the legendary, very beloved binary search tree, which has additional rules on top of a binary tree. So you'll see here that these numbers are slightly different, and this is actually, in fact, not a binary search tree, which we discussed on the stream last time. And so the reason for that is a binary search tree is a tree where each node has at most 2 children, so it is a binary tree. And specifically relating to the values, the left child is less than the parent, and the right child is greater than the parent. So for 7, everything to the left of 7 has to be less than 7, and everything to the right of 7 has to be greater than 7. So you have the 15 here and the 2 here, that makes sense. But that has to be true for every node, not just the root. So 2's left child would have to be less than 2 for this to be valid. But it's not. It's 3, right? So this is a binary tree, but this is not a binary search tree for that one reason. This interaction does not work. If we change this to a 1, it would be fine, but we'll leave it for last time. Now we took a quick jump after understanding those to talk about recursion. Recursion is very big brain, kind of hard to wrap your head around. So if you don't get it already, you might not get it now. Don't worry about it too much. But the basic idea is the simplest version of recursion is this. Function forever calls function forever. What happens? It runs forever, right? And the error that you get is a stack overflow. Now, if you wanted it to not run forever, you could write the not forever function, which will still call itself, but it'll change the value. So if I call not forever with 15, it'll take in the 15, and it'll subtract 1 and call itself again. So it calls itself with 14, then with 13, 12, 11, all the way up to 1. When it hits 1, we have a condition here, this if statement. If x is 1, return true. And that's what's called a base case, which is the end of the recursion or the point at which recursion stops, right? And the meme is, the definition of recursion is recursion, or to first understand recursion, you must understand recursion. Or in programming, just a function that calls itself, right? Don't overcomplicate it. This is recursion. Literally, this is the whole thing. And the only real concept you need to super understand is the concept of this base case. It stops you, right? A very traditional version of recursion is down here, factorial, right? So you might be familiar with factorial being, oh my gosh, 5 factorial is 5 times 4 times 3 times 2 times 1, right? And you can implement that with recursion like this. So if I did factorial of 5, it'll return 5 times factorial of 4, right? 5 times factorial of 4. And then factorial of 4 would return 4 times factorial of 3. Factorial of 3 would return 3 times factorial of 2. So on and so forth until it gets down to 1, and 1 will just return 1 and do the math all the way up. The big dangers we discussed, and our favorite meme was when talking about iteration versus recursion. Why do you do a for loop instead of recursing if you can? The basic premise is call stack bad. And the idea of the call stack is, in some languages, what will happen is basically every time that you call this, it has to store x, right? And remember what it was. So for the call on 15, it has to remember and store that 15. For the call on 14, it has to remember and store that 14. 13 has to store that, so on and so forth, which doesn't seem like a lot, but you keep looping, you keep looping, you keep looping. Eventually, you've stored a lot. So you get this tiny brick of memory for the 15, and then another tiny brick of memory taken for 14, another tiny brick of memory taken for 13, all the way up to 2, 1, and then it stops. And then all of that memory clears as it goes back up to the top, right? And this is called the call stack. It is a stack of the little data stored in function calls, right? So every time you call this function, you get this little bit of storage on here, which is why we have the legendary error stack overflow, right? This error comes from when the call stack gets too big, because you called function forever, and it will make these little bricks of memory forever until it eventually runs out of space, and there's nothing left in your memory, and it will just, and the stack that is memory will overflow, will grow beyond its own limits. We also very quickly discussed tail recursion, which is a strategy, some languages implement tail recursion being effectively, instead of storing the x is 15 here and 14 here and 13 here and all of those little bricks in memory as you go up the call stack, what it'll actually do is make one brick of memory and then just keep adding information to it. So at first it stores in the memory, hey, the answer is going to be 5 times whatever factorial of 4 is. And then when it gets to the next recursion, it says, oh, okay, actually it's 5 times 4 times whatever factorial of 3 is. And it keeps a running total instead of having to go all the way back up, right? So in this case, you had to get all the way down to 1 and then return to 2, return to 3, return to 4, 5, 6, 7, 8, 9, 10, 13. So you needed to store all of this so it remembered all those functions. But the magic of tail recursion is you don't have to do that, right? It kind of just keeps one running total and then throws it all right back up to the top. It just jumps from here, way back up to here, just like that. So if you're ever asked the question, the legendary question, the super common question of why would you ever use iteration versus recursion, the short answer is call stack bad, which became a giant meme. So if you iterate, if you just do a for loop, you don't have to store all of this stuff, right? You're not making all of these new little chunks of memory as you call functions. You're just doing the math, right? And that's much easier on the computer. So this is the meme. If they ever ask you that, the summary of your answer is call stack bad. Whew. All right, and then we got, okay. So then we talked about traversing a binary search tree. We come in, right, and the question I gave was print a binary search tree. And the way I will give you the tree is the root node. So all you have is this piece of data and nothing else, right? You get a data of 7, a left of node 2, and a right of node 15, right? Which is what this tree is. And if you look through this tree, you'll notice it follows all of the rules of a binary search tree, right? To the left of 7, all of these are less. To the right of 7, all of these are greater, right? So 2 being less, but 4 being greater than 2, 4 is on the right of 2, right? And 1 is on the left of 2. So it keeps that rule. Left, less, right, more. That's it, right? Right, more, right, more. Wait, tail recursion behaves like a for loop? Like it keeps making memory blocks? No. For loops don't keep making memory blocks. Recursion does. Calling the same function over and over again. This function that keeps calling itself, that does that, right? A for loop, you'll just use a variable normally. Tail recursion kind of simulates that. It's something you can look a lot into. It does get quite complicated. So we came up with a simple function print tree, right? And the idea was this is a recursive way to print our own tree. So if the node that we're given is null, dodge out, print our current node, right? So I hand you the root, so it starts and it prints 7. And then if we have a left, call the same function on the left, and if we have a right, call the same function on the right. So the output of this ends up being here, right? And we can run through this very quickly. So I call print tree on node 7, right? It's not null, so it prints 7. Then it's going to say if root.left, print tree on root.left, right? So we've called 7 itself, and now we're going to call the left half of 7 here. So at the bottom here, it calls 7, and you each call the left recursion and then the right recursion. So this gets a little annoying to track, but this is just the basic idea. So you call 7, and then it calls, so print 7, then it calls root.left is fine, so print tree on 2. So that's going to print out 2, and then call the left of 2, which will print out 1. And then now that it's finished the left half of 2, and there's nothing left to go here, it goes to the right half of 2. prints the 4, right? Comes back up. So it's this recursive left and then right. So this guy says, I want to do left and then right. First I'm going to do left. This guy says, I'm going to do left and then right. First I'm going to do left. This guy says, I'm going to do left and right. Done. There's nothing there. We come back up. This guy says, I'm done with left. Going to do right. Does its right. Comes back up. This guy says, I'm done with left. Going to do right. Boom. This guy says, I don't have a left. I'm going to do right. This guy says, I have nothing. Right? And so that's what gets you your order of going all the way down the left, back up like this. So 7, 2, 1, 4, 15, 16. Simple. And we branch that out into what are known as the 3 traditional tree traversals of binary search trees, which have different terms. You can either call them, hopefully you can see this, pre-order, in-order, or post-order, or prefix, infix, and postfix. However you choose to word them. Generally you use the orders because it's the order of the traversal. But yeah, these are the basic ideas. So the basic idea here is, with these 3 different traversals, right? Who said I had to go parent, left, right, right? Like, who said this order is important? So really we have 3 different values here, so we actually have 3 orders that we can do, assuming we keep left and right in the same. So we can print parent, left, right. Then we can print left, parent, right. Then we can print left, right, parent. So initially we said print 7, then print all my left kids, then print all my right kids. But what if I said print all my left kids, then print 7, then print all my right kids? Or if I said print all my left kids, print all my right kids, and then print me. And so the basic idea here is, at a very high level, this is what those functions will look like. But basically, the big takeaway from this was all of these will come out differently, right? So if you do it pre-order, this is the output you'll get, which is what we did above. Left, like print me, and then print left, and then print right. And then if you do post-order, which is the opposite, so the parent goes last. So do my left kid first, then my right kid, then me, then my right kids, right? And then me, sorry. So then you come out with 1, 4, 2, 16, 15, 7. But the magic of the in order, which was do all the left, then do me, then do all the right, is that in order actually gives you order, right? These values are in ascending order. And the reason for that is this function literally says, right, when you do print the left one and then me and then the right one, you're saying print everything less than me, then print everything, then print me, then print everything greater than me, right? It's very straightforward if you think of it like that, but it can be hard to see it in the code. I'm going to start us off with a heap. Once you get through a heap, you're going to feel like graphs are a cakewalk. So I'm going to save graphs for after heap, because then you'll feel really good when you get graphs. All right, so I'm going to call these medium data structures, because this is slightly, I wouldn't call these as simple anymore. All right, the legendary heap. Let's go copy our tree. Whew, okay, so heaps are where you really get this interesting middle ground of a bunch of other concepts. I want to copy, what am I trying to copy? Where was our binary tree definition, right? So let's come back up and let's remember what a binary tree was, right? All we defined it as is a tree where each node has 2 children. It's got a root, maybe some leaves, not much else, right? Now a heap is going to be a very, very special tree. A very weird kind of binary tree. First, a heap is a type of binary tree. All right, so I'm going to just say a few things about heaps, and these won't make a ton of sense until we get into it, but write these down because they will be important. Heaps are not inserted into. They are filled in. Now, let's just say heaps are filled in from the bottom left. To right. Okay, for the data structure stayed for the B Canvas tutorial. Cheers. Yeah, let's make. Can we get these to be bullet points? Actually, so this is gonna be really weird. So you'll actually remember. Oh, okay, yeah. Heaps are filled from the bottom left to right. So basically, when you think about this tree, this is not a heap. And this can't be a heap because it has not been filled from left to right, right? Here, there should be a left child, right? Because there is not a left child here, this is not a heap first. There are other rules, but first, let's fix that. Oh, jeez. So basically, I'm just going to drag this guy over here and drag this guy over here. Ooh, look at those arrows. It was almost moving on its own. And now this is going to be the left, obviously. We can actually cut these out because you guys understand that to the most part. But basically, if I come into here and I wanted to add 16 to this heap, the only way I can add 16, the only place I can add 16 is at the bottom in this exact spot. It can't go on the right where it was, right? It can't be over here because then that's not a heap, right? It has to be added here. Now, remember that. It's going to come up a lot later. Now, there are two main types of heaps. I have to say main because somebody somewhere will be a giant butt and call out some really obscure stuff. And so I'm going to say two main types of heaps. There is a min heap and a max heap. Each heap follows this rule. The root of the tree or the top of the heap is the min or max of the entire heap. So if it's a min heap, this is always the smallest number in the heap. If it's a max heap, this is always the greatest number in the heap. So right away, now with that new rule, looking at this, is this a heap?
No.
Why not?
The root, well, 7 is not the minimum value. Mm-hmm. If we were to try to say this is a min heap, and it's also not the maximum value.
Beautiful. Let's swap it up a little bit. Let's give ourselves a 1 here. Let's give ourselves a 7 here. Is this a heap?
Yeah, it would be a min heap.
Good.
I have a question. So when I'm adding a new node to my heap, how come I can't add it to the left branch of a leaf node? Why does it have to be added to an available left slot of a non-leaf node?
So allow me to clarify here. The key term here is like filled in. So you cannot have an incomplete level in a heap. You must finish each level.
Gotcha.
Right? And so the idea here is like, if I came in and I just had this, the second level is not finished. So I have to fill it out. Right? And then when I come into the third level, there are 4 spots here. I need to fill them all out before I can get to the next one. And they have to get filled out left to right. One of the other important points to note, in the same way that for every node of a binary search tree, that node has to be its own tree, right? Every node's left child has to be the least, and every node's right child has to be the least. For this, instead of just saying this, each node is the min/max of itself and its children. This is another way to word that. Okay? So I want you to look at this, right? 1 has to be the min or max of itself and all its children, right? So 1 has to be the least of this whole heap. All of its children, grandchildren, etc.
Oh, and does that apply to the following level?
Each node, yeah. So that's what Dan called out, is that I said root instead of node, which is my bad. I apologize for that. So for 1 has to be the least of all of these guys. But it's actually super interesting. If you know for sure that 2 is the least of itself and its 2 children, and if you know that 15 is the least of itself and its 2 children, then all you need to know is that 1 is the least of itself and its 2 children. Does that make sense?
Right.
So if this guy is the least of these 3, and this guy is the least of these 2, then 1 only has to be the least of these 3. So I said here, children, grandchildren, etc., right? And I'm stretching into the chat window a little bit, which is... I'll try moving this down here. That'll probably be easier. But realistically, it should only have to be its children, assuming everyone's doing the right thing. Assuming everyone is correct, right? So, here's the big thing. The key with a heap is there's a handful of algorithms that we talk about. Now we're going to talk about heap sort, right? So here's the idea, right? If I tell you that the top number is always the lowest in the heap, and that's always true, if you wanted to sort a bunch of items, right, sort everything in the heap, least to greatest, all you'd have to do is say, give me the top, and then let the heap fix itself somehow, and then say, give me the top, right, because the top's always the least. And you just keep saying, give me the top, give me the top, give me the top, until you run out of items, right? And each time you got the lowest one. So you'll get 1 somehow, and then you'll get 2 somehow, and then you'll get 4 somehow, and then you'll get 7 somehow. Because at each point in time, that'll be the top. The idea is, so long as that statement is always true, the root being the least, I can just say, chop off this thing's head, and give it to me. Now, we're going to talk about one of my favorite algorithms with one of the most fun names of all algorithms, which is Heapify, or just the heap sort. So the heap sort requires using 2 different forms of Heapify. And this isn't always what it's called, but this is what I call it. And so I describe it as Heapify up and Heapify down, which will make sense in just a minute. But really quickly, let's define our heap sort. So again, I'm going to give you the node root, right? Or actually, how do we actually pass this? Oh, I got to remember. Let's just say heap h and not think about it too much. And we'll get to the actual code later, right? But heap sort is basically while h dot is not empty, right? And this is just pseudocode. Print h dot pop, right? And that pop's going to take from the top. Right, okay, so when you pop for a heap, so just very quickly, just think of pop, which is just going to remove top, return top, return the old top, and then fix heap. I'm just going to say that, right? That's what our pop looks like. And so, assuming that this works, right, while h is not empty, print this one. It's going to print 1, right, take off the top, return it, fix it, right? And then once it's fixed, 2 will be at the top. Do it again, do it again, do it again until it's not empty, right?
Wait, why is 2 going to be at the top and not 15?
This is a min heap, minimum heap. So we want the lowest number at the top.
Okay.
When we're about to write basically the code that's going to do that, right? So now here's the thing. In order to fix this heap, there are kind of 2 scenarios that we'll have to do. For the heap sort, we only have to do 1. And this has always been one of my favorite algorithms to talk about. Here's what we're going to do, right? Now, everybody, I want you to stick with me here for a second because this is going to get obscure. But this is how I like to explain this. Now, are you all familiar with this animal? Wow, it really just showed the food. That is so unfortunate. Hopefully you are all familiar with the chicken. The chicken is a well-known animal for its food and its eggs, correct? Now, here's a horrifying fact you might not know about chickens. This is going to get dark. When you cut the head off of a chicken, it does not die immediately. It will run around and stay alive for a few minutes. Now, in my world, in the world of Frankenstein chickens, when you chop the head off, the only way to save the chicken is, can you guess?
Put a new head.
Yes, put a new head. And what's the new head gonna be? Its foot, exactly. So, as we remove this head, right? I say pop the first time and it removes 1. we are going to go to the bottom of our chicken. Down here, where it has all of its feet. And we're going to grab the most bottom right foot and whoop it right up to the top. Now, our chicken is alive. It's alive. But is our chicken a heap? Is our chicken a min heap right now?
No.
No. Why not?
This is not the minimum value.
It's not the minimum value. So how can we fix that? Right? How can we take a heap that is wrong and fix the heap to be correct? Now here's the real question. What part of the heap is wrong? Is the whole
head?
heap wrong? No, it's just the head, right? Our weird foot head monstrosity. We know that the head, the top of our heap, is the problem. So, can we fix the heap top to bottom? Here's the question I'm going to ask you, right? Let's go back to our old heap. Now let's take a good look at this. Now remember what we said earlier. The magic of this heap being recursive, right? Of knowing that 2 is the least of all of these, and knowing that 15 is the least of 2 of these, means that 1 only has to be the least of these 3 numbers, right? Because the rest just works. The rest is all greater by definition, right? It's that kind of recursive concept. So, if I delete 1, where do you have to look? Without knowing the values, where do you have to look? I'm actually going to do it this way. Where do you look for the lowest number?
The children.
The children of the head. Those are the only 2 places. The least value in the heap has to be either 2 or 15. And that's it. There's no other value it can be, right? By definition. So long as this is a valid heap, so long as we keep this heap valid, there is no other place that we ever need to look. Let's think about that. There are only 2 nodes that I have to check, right? So, here's what I'm going to write. We're going to call this heapify down. Okay? And the reason we're going to call it heapify down is because we're starting from the top, right? And we're going down. Now, let's delete this. I'm going to give you node top. Or, I'll even call it root. Or, no, we said top. Let's just call it top, right? Now, think about this. I have 16, I have 2, I have 15. What do I need to do in order to fix this heap? Would you like to write pseudocode for this?
Sure.
Write whatever you want, and then we can come in and fix if we need to.
Then we can evaluate.
Yeah, so keep in mind now, this pop function is not what you're writing. What you're writing is just the part that fixes the heap. I'm giving you exactly this. You are getting this tree, this heap exactly as it is, and I just need you to fix it. Don't worry about popping. Don't worry about returning. Just fix the heap.
What happens to node.data after we replace it, right? So in this case, right, we have 16, 15, and 2. We'll take 2. We're going to replace it as our head node, right? Now the question that I have is what's going to happen with 16? What's going to happen to that node? Where does it go? How does it know where to go to?
If I told you this was a recursive function, if I told you to think about how you've done your trees a little bit, right? You've run this algorithm on this set of 3 nodes. And you put 2 up here. What can you do? How do you use the code you've already written to answer the question you just asked?
Did you set it like with an infix?
Don't worry too much about the order. Literally look at the code you've just written. What does the code you've just written do?
It just replaces basically the head node with the with the minimum value node.
Okay, great. And what do you do with the 16? Because that's still in our heap. It has to be somewhere. Don't overthink this. There's only one place that doesn't have a value right now. You've stolen the 2.
Oh, and that would be so. Okay, so if I stole the 2, then I would put the 16 where the 2 is.
And then, have you won? Have you finished your work? Let me swap these for you. So let's say you managed to get that to happen. Now what?
Yep.
Is this a heap?
I would say no. That this is not a heap.
Why not?
Because the left kind of 16, 7, 4, 16 is not the minimum value between 7 and 4.
So what can
Or
you
it's not the minimum value between those three.
So what do you need to do?
So then in that case, I need to recursively call heapify down again.
You got it.
That's it. So that's the recursion factor of it, right?
But once you got that, write your recursion. What do you recurse on?
Okay, so you gave me no top, which in this case, so if I'm starting from the top, right? 2 is no top. It goes down. Between 2, 16, 15, it's a heap. But between 2, 16, 15, 7, and 4, it is not a heap. Because we need to call heapify down on the 16 node. We need to recursively call that function again as 16 as that top node, because it needs to then fix itself amongst 16, 7, and 4. So then how would I do that?
Write it in English
so
first.
what should I do with this sentence here? With the find min value node dot data, what should I do with this part right here, like the second portion, below the return?
So
Should I just delete this?
here's what I would say. Replace is not necessarily the word you want. What you described, I would say, is more of a swap.
So let's say we swap it, right? So let's say before it was 16.2, so we swapped it. That's how it is currently. If we look at our diagram here, then could we call? No, yeah, we could. I'm totally sure we could. We could call heapify down, right? So this is after our swap happens. So after we swap, we have to call heapify down on. So we swap node.data with found min value and set root. So then what should we pass into our heapify down function? It would have to be like
Feel free to start out in English.
would it be node dot left? Like it would be if I'm looking at the diagram, but how would I know if it's node dot left or node dot right? Is it because a heap goes from leftmost first? Is that why?
So let me give you a slightly different example. What if, and ignore the other parts, but if I gave you this instead, which one would you have to recurse on?
The 2.
Right.
You'd still swap the 16 with the 2.
Yeah, right? And so, is that right or left in this scenario?
Right.
So, is it always left or always right?
No, it's always the one that's at the least the minimum value.
Bingo. That's it. This is where the pseudocode gets a little annoying, but it just comes down to an if statement there.
Right. Oh, would it be 2 if statement? Like, would it be a nested if statement or?
It just depends on like. So we
Okay,
just
so-
said
so-
find minimum, but like if you knew which one was the minimum, you would know if it's left or right.
And you pass that into the argument, right?
Yeah, exactly. So you can just write for the pseudocode left or right, whichever is
Gotcha.
least.
Okay.
But that's the basic idea.
We swap it. So we swapped it to. Okay, so here, if I take control, right? So 16 is our node, our root node. We look at 2 and 15, and we're like, oh, yo, this 2? Nah. Oh shit, I'm definitely gonna muck it up. Okay, Dan, I totally screwed the drawing, but I apologize. So the 2 gets swapped to 16, and then from the 16 point of view, I have to look at the 7 and 4, right? And in between 16, 7, and 4, I'd swap the 4 with the 16. And then that would that be it? Okay, so if I look at this, 2, 4, 15, 7, 16. Is this a heap? I'm going to say yes.
Yeah. So just to make some slight edits here, just because of your pseudocode, you wrote dot left, but not like left to dot data. So I'm just gonna say contextually top dot data and right dot data here, because technically it would have been no dot left dot data, no dot right dot data, but a little annoying. But yeah, Rodrigo called that out. So this is why pseudocode. That's why I try to say like do it in English as much as you can. That is the most basic version of this. Now, that has allowed us to sort with a heap, right? Now, we're going to take a step back here. So this was a little complicated, right? But really starts to understand the recursive nature of the things that we're doing. So what I'm going to do really fast is I'm going to pop us back to binary search trees. And we're going to very quickly talk about how you add, remove, and insert into a binary search tree. And then we're going to come back to heaps and see how those 3 operations differ. Sound good?
Okay. Yep.
Binary search tree. Left child is less. Right child greater. Right? Basic rule. That's it, right? This is less than this, and the right is greater. But all to the left of this are less, all to the right of this are greater. So remember, throw out the heap for a second, bring yourself back into binary search trees, top to bottom, no left to right, much simpler, a little bit easier. Now, let's talk about our operations here. 3 operations. Add, remove, delete. 1, 2, 3, and let's talk through how we do them. So, adding to a binary search tree. Let's go to a new line. Good. Top, down. So, as always, the way that you are given a tree is the root. The only thing that you get is this happy little guy right here. When I give you a tree, I give you the root. Adding to a binary search tree, right? Key here is that when you start with the tree, you come in from the top. Start at the root. Now, super simple. If I told you I wanted you to add 12 to this tree, what do you think? How would you do it? Or do you want me to just take you through it? It might not be
just quickly saying.
Yeah.
No, just quickly saying. I would say you take the 12, right, and then you compare it to the value of 7 because you start from the top. If the value is less than, if the value is less than 12.
Keep going.
Oh, okay. Yeah, I would just compare the value of 12 to every node that you're iterating through, right? Because you want 12. If you basically want to keep the order of your binary search tree, so you want to place that 12 in a position where it's less than or greater, or it's greater than the 7, or sorry, I'm talking gibberish. You'd see if the value is less than or greater than 7, and then depending on that result, you place it on the left node or the right node, and then you repeat, you reiterate that process again.
So take me through 12. 12 comes in. What do we do?
Yep. 12 comes in, compares 7 with 12. 12 is greater than 7, so we put it on the right portion of the node because of the definition of BTS.
BST.
Left child is less, right child is greater.
Good. And then where does it go?
Now we compare 12 with 15. Since 12 is less than 15, we put it to the left.
And now what?
And that's it.
How do you know?
Because it's no more children.
There you go.
It is the child.
When the parent doesn't have the child you're going to, when that child is null, there you go. So that's an add. Start at the root. If new node greater than root, recurse, recurse on right. If new node greater than or less than root, recurse on left. If root is null, make this node child. And that depends, right, on which way you're coming. But that's the super basic idea, right? You either go right or left, you go right or left, and then you tie yourself in. This isn't even pseudocode. This is just conceptually what you're doing. Now, removal. A little more complicated. I want to take 2 out of the tree.
What is the difference between removal and delete?
Nothing. Oh, wait. Oh, sorry. My brain is small.
I don't know okay, so what I'd basically do, if you want to remove 2, we'd would compare the value of 2 to the value of node.data. If it matches, then Oh, I see why it can be complicated.
So let me actually take you through this one because I'm going to kind of get out ahead of this.
Okay.
This one gets weird. And understanding why this is weird will
Okay.
be important later.
Okay.
So I'm going to move this ladder.
I can see why it's weird because what like I can see why it's very weird.
Yeah. So I want you all to imagine right now. So this gets kind of complicated, right? If I told you I want to remove 2 from this tree, what the heck do you do? What?
Yeah.
Look at this. There's all these kids here. Like, what do I even... In fact, let me make this like... Let me make this 2, and then let me give myself like a 1.5. Just to make it even more complicated. So that there's no obvious
Okay.
option. Like, how do I... Right? And so now, very quickly, this deletion, woo, gets uncomfortable. You're like, oh, well, I mean, if I remove it, like, somehow I have to move data there, right? 7 needs a left child. So, like, what becomes 7's left child? Do I take the 1 and just put it up there? And if I put it up there, how do I rotate? Like, how do I move? Do I have to move 1.5? Because then 1.5 has to be on the right. Do I have to put that here? Ooh, that one's tough. And it's like, oh, do I take the 4? I could put the 4 up here, right? Like, I could do this. And this is, like, technically correct, right? But then I'm going to have to move more stuff around. So it gets a little uncomfortable. So, here's the idea. If I move 1... Oh, yeah, sorry, hold on. I think I want... Yeah, no, this is good. Okay, sorry. So, if I move 1 into the 2 spot, what do I have to do with 1.5? Just high level. Is 1.5...
Right now, 1.5 is... So if 1 is our root, right, then 1.5 is root dot right.
Correct.
Of it's root dot right?
Yeah.
So if we were to put 1 and replace it with 2, then that 1.5 has to become, instead of root dot right, it becomes root dot left.
Ooh, but it can't. 1.5 is greater than 1. Right? So this gets really messy.
Shit, dude.
So somehow you'd have to insert this guy into this tree and like re-add this one in here, right? Very messy, very quickly. Just understand that that's messy, right? And that's why we don't want to do that, okay? So,
Okay, yeah.
now let's talk about 4, right? If I tried to do it with 4, you're going to get a very similar problem. Where I'm going to try and move 4 up here, right? And now 4's still got 3 on the left. And 3's got to be on the left. So now I'm going to have to somehow take this 3 and put this into this tree. And so it's going to have to go through the 1 and then like through the 1.5 and insert it down here. And that's going to get messy. But now here's a really big question. What if I took 1.5 and put it up here? Does that work? Is that okay?
Yeah.
Okay. So the tree's valid, right?
Yes.
Cool. And now what if I took 3? Same question.
This is also valid.
This is also valid. Interesting. Right? Now, allow me to make this just one step more complicated. Gonna give myself a... so help me God, bCanvas. Give myself a 5. If I put this 5... Oh, I'll delete this. What if I put this 5 up here? Does that work?
Yep.
Does it?
No, it doesn't. Sorry, I jumped the gun. It does not work.
Doesn't. Interesting. And now I'll do one last one. We're running out of space a little bit here.
Oh, what?
If I make this a 0, they also apparently you can make these smaller. That would have been helpful. Oh, sorry, hold on. This is the stream won't be able to see these. I'll need to move these guys up just a bit. Now, if I made this 0, right? If I have this 0 here, if I try and put this 0 up here, does that work?
No.
Why not?
1 is not less than 0.
1 is not less than 0. So that's so interesting. So why would it work for 1.5 and work for 3, but fail, oh my god, for 5?
It must be the
I fail for 1.
it must be the property of the grandchildren based on where you're picking them from.
It's something to do with that.
So like if you use the right node of your left child, you'll balance it. And if you use the left node of your right child, you'll balance it.
You're very close.
But you won't do it if you use the vice versa.
You're so close. What you're saying is almost correct. But what if the tree kept going?
Okay. It'd have to be the leaf then.
Interesting, right? And so I'm gonna continue making this more complicated because it's necessary to understand this. And this is why I wanted to avoid doing this one last time, because this gets kind of really up its own butt. Can you guys still see the smaller nodes? The text should be the same size, so I'm hoping this is fine. Let me know.
We can also give them a link. We can also give them a link to this. So like
if we give them the link, then we'll see their cursors the whole time.
Oh, okay. Sure. So we'll wait after stream.
Yeah, after stream they'll get the link. Yes, should be good.
Gotcha.
Yeah. So now let's add a 3.5, and let's add like a 2.5, right?
Mhm.
Oh my god.
Wait, what?
Trees keep going. Trees don't stop.
Yo, this is so fried. I know, but like, this is so weird.
It's very weird, and it's gonna be really complicated right up until it makes a shitload of sense, right? So now pay very close attention here, because this is by far probably the most complicated thing we'll have done so far, right? Which of all of these can you put up here properly?
Well, you could put the 2.5.
Okay.
You could put the 3.5, and you could put the 3.
So, what is the least work? Also, really quickly, let's just analyze each of those and see if they're correct. Can I put the 2.5 here, right? So if I replace this with 2.5 and I deleted this guy, really quickly, is this valid?
Yes.
Cool. And then let's just take the 3.5, put this up here. Is this valid?
Yes.
Great. Is it though?
1 is less than 3.5. 4 is greater than 3.5.
And what about the rest of the tree?
Oh, well, why does that matter? Because, okay.
Not a heap, it's a tree.
It's a tree, right? Yeah, so then that would not be valid because the 3 is less than the 3.5 node.
3 is less than 3.5. 3 has to show up on the left of 3.5.
Yeah.
So that one doesn't work. So this is the only node that works. Right? That's super interesting. Getting somewhere.
Yeah, it is.
We're getting somewhere. Hold on. Now, I'm going to go one last step further. I'm going to add a 2.75. Really should have picked bigger numbers for this. Can stream still see this? Yeah. Right? Now, can I put 2.75 at the top?
No.
Why not?
The 2.5 is less than 2.75.
Correct. So, this whole side, there is exactly one node that we could replace 2 with. And we called it out already. Which one is it?
It's the 2.5.
It's the 2.5. This is the only value on the right side that we could replace 2 with. Now I'll ask you, let's say that we took some inspiration from what we did with that heap, right? What's up, Hal? Now let's say for just a moment, right? We cut out this 2.5 because we're deleting the 2, right? So we put the 2.5 here instead and we throw out the 2. We've agreed that this is just about valid, but something's broken, right? 2 had a kid. What do we have to do with this 2.5 now? 2.75 now.
It has to become. It just take. It has to take that spot.
What spot?
The one we just took from the parent spot.
Right here?
Yeah.
Is this a tree?
It is a tree.
Interesting. We just made a deletion. It looked super weird, and it felt really uncomfortable, but looking at this tree, can you describe to me how I could have told you right away that 2.5 is going to be the only node that we can put up there? What is it about 2.5's position that makes that true?
Wait, hold on. Is that a valid statement? Because we could also put 0
on the right side. Just looking at the
in
right
that position.
side. Just looking at the right side.
Just looking at...
Pretend none of this is here for this moment. Just for the sake of argument.
Okay, fine.
Just for the point that I'm making.
Right. Okay. Yeah.
So, describe
the way we could look at that. Yeah, it's just the smallest value. It's the smallest node value we have on that right branch.
On the right branch. It is the smallest value on the right. Now remember, let's look at the left really quickly. What of those 3 values can we put up there? There's only one value on the left side.
0.
Not 0. If we put 0, 1 is greater. 1.5 is greater. Right? Which of these 3 values can go here?
Hold on. So if we replace the 2 with 1.5, 1 is less than 1.5, 4 is greater than 1.5. Yeah, we could put the 1.5 there.
You can put the 1.5 there. Interesting. Now, describe the 1.5 to me. Why is it the 1.5?
It's the greatest value on the left branch.
It's the greatest value on the left.
Get the hell out of my face.
Now, Asbjorn, you said recurse left until you find a leaf. I want you to be careful. Is 2.5 a leaf?
Dude, Dan, I actually hate you.
Yeah,
like,
you should.
I actually hate you.
Melky, really quickly for me. Is this 2.5 a leaf?
No, it's not.
No, it's not. But it is the least value, right? So, if it's the least value, we always know what about it. I'm just going to tell you this one because this will be a little complicated. But the least value on the right side won't be a leaf, but it can only have 1 or 0 kids. Because if it had a left kid, we would have gone there because it would be less, right? So this last node, the one that we swap from, can't have a left child. Does that make sense? If 2.5 had a left kid, we would have been there, right? We would have taken that value instead. But it's not there. That's how we know. Make sense? It's okay if it doesn't. Let's run through it again.
It makes sense. It's just a lot to take care.
It's a lot. So let's go back to the big light bulb moment. The left, as Kittle said, the leftist on the right and the rightist on the left. Or the smallest that's higher, or the biggest that's lower, right? There are exactly 2 values you can look at, and those are the 2, right? Now it depends on the actual tree. If you don't have anything to your left, then you're going to want to go to the right tree. If you do have both a right and a left, take your pick, right? And we always know that that last guy will have at most 1 kid, which is great, because that means when we actually go do this swap, when I pull out 2.5 and I blank it out and I delete my 2 from the tree, which is what we're doing again, and I put 2.5 here instead, I know I can just move this child right here. Right? That's always safe. And I can say the same thing. Right? Now, my wife now knows my handle, the feels. Now, think about this. For 1.5, is 1.5 allowed to have left children? Is 1.5 allowed to have right children? If we take 1.5.
It's allowed to have a left child, but not a right child.
Good, because
a right child will continue, it's greater than 1.5, which would make it then the child that we want to replace it with.
Boom. Beautifully said. Could not have said it better myself. Absolutely correct, right? So we could have this 1.25, right? And that's allowed to be there. But if there were a greater value, we would have taken it. And so same thing. If I took this 1.5, right? If I took this 1.5 and I delete my 2, as we just so badly want to because we hate 2. Please hold. Now, if I take this 1.5 and I put it where our 2 was, I can delete the 1.5, and I know confidently I can replace it with the 1.25 because that's the only other job. Probably. Now, here's another question. Is 1.25 allowed to have children? Oh, crap. Hold on.
Is 1.25 allowed to have children? Yeah, I don't see why not.
What kind of children is it allowed to have?
Well, it still has to follow the behavior of BST, right? So the left node would have to be less than 1.25, and its right child has to be greater than 1.25.
So,
Wait.
one level deeper. Let's think about it.
Uh-huh.
Sorry, these the tiny arrows are really getting me. I'm gonna go ahead and just delete this whole thing. We're just gonna move all of this over a bit. One level deeper. 1.1 and 1.3. I apologize for the decimals, everybody. I did not have the forethought to make these very big numbers. Can I still just move 1.25 there? Do I need to move any other nodes around?
No, you can move 1.25 there.
I can just move it there.
Yeah.
I can literally just move it there. And the reason that's true is because 1.5 did not have a right child.
Right. Yeah.
If it had a right child, that would have gotten a lot more complicated very quickly. But it didn't. And it can't. So, we can confidently say, no matter what's underneath this one, to move it here. No matter what's underneath this 2.75, we can move it here. Right? Always, always, always. So, we come into our remove. Now, Melky, what is your favorite direction, left or right?
I'm more of a left kind of guy.
More of a left kind of guy. Bad choice, but we'll take it. So,
Alright.
First, find the node. Find the greatest node. Or I want to say the greatest left child, but that's dangerous. Greatest node on the left of our node. Find the greatest value on the left, to the left. We'll say to the left of our node. Swap current value with lowest value. What is that? Move up any children. Oh, dude, what? Oh, Astro, thank you so much for the bits. Holy crap. Oh, that's so kind of you. Thank you, I really appreciate that. Oh, you didn't have to do that. Thank you. I hope this is helpful. Yeah. Oh, thank you so much. That was really kind of you. Aw.
Astro, you crazy, Astro.
Astro support. We love Astro. Everybody make sure you give some hearts to Astro. We do love. We love the community. Yeah, I'll do it too. Bam. Move up. Left. Or sorry. Swap left child of greatest. Or replace greatest with left child, if any. Boom. A perfectly valid algorithm. Now, finally, what if there are no left children? What do we do?
We go to the right.
Now, I don't want to write any more code. What do we do? I want to replace 2. I'm going to delete 2. What do I replace it with?
Instead of saying find the greatest value to the left of our node, it'd be find the smallest value to the right of our node.
Don't even think about that. This is the specific case where there's nothing on the left. What do we swap it with? And don't say 2.5.
You wouldn't be able to swap it with anything.
There's exactly one node. Well, there's actually multiple. But no, sorry. There's exactly one node that you can put there with no effort. Nothing changes. Remember how we were able to put the greatest with its left child guaranteed? Why was that?
Yeah.
Why were we able
Greatest.
to do that?
Oh, because it didn't have any more right children, so we knew that it didn't have any more values greater than itself.
Right. And you could have done the opposite, right? Here, we know we can replace 2.5 with 2.75. Why?
Right. Because there's no value less than 2.5. 2.5 doesn't have a left child.
Interesting. So if I asked you, what can I replace this 2 with if it doesn't have a left child? What's the right child?
I mean, you could. It's 4.
It's 4.
But I mean, like I would probably challenge that. Like why? Like you could put
With 0 effort. Can I just do
yeah,
this?
yeah, it'd be 4.
Does that work?
Yep, you can. Yep.
That's it. Keep in mind very clearly, we made the choice to find the greatest value to the left, right? We proved out in no uncertain terms that we could have done it the opposite way. But if no left child, replace current node with right child. And finally, what if there are no children?
Sorry?
What if there are no children? You lived a long,
What do you mean, like,
happy life, but you, as a node, have had no child. You are just a 2 in the breeze, ebbing and flowing as the world changes around you.
oh, then you can't. Well, then you can't remove it, or you just remove it. You just get rid of it.
Remove it. Just yeet it. No children. Just yeet current node. This is add and remove. I'm not really going to go through the insert in particular and everything. Some people, like sometimes there's an insert if you want to insert to a certain spot in the tree. Not super common. I won't worry about that. Basically, if you can add from it, if you can delete from it, that's a win, right? Now that we've seen all of this, now that we understand all of these operations, we're going to context swap again. Boom. Back to, you know them, you love them, they're legally chickens. Heap operations. Boom. So, let's grab this lad. Drop him down here. Now, let's put ourselves back in the heap context. What do we know about heaps? Give me the rules, Melky.
Oh Jesus. They are. You have to fill them from leftmost, from bottom left, and they are essentially ordered by minimum or maximum values.
How are they ordered?
The root has to be the min or max value.
Perfect. Beautiful, beautiful, beautiful.
I'm learning, Dan.
You're learning. Look at you. Now, let's take this guy back up here. Take this guy back up here. Is this a heap? And if so, what kind of heap?
2 is less than 415. 4 is less than 10. This is a minimum min heap.
And is it a min heap?
It is a min heap.
Cool. I agree. Pretty good looking min heap. Best min heap I've seen all day.
Yep.
Now,
Good one.
earlier we talked about popping. If we wanted to pop, remove the top and fix it, what did we do?
We cut its head off and then we put a foot on its head.
Which foot?
The smallest foot.
Wrong answer. This ain't a binary search tree. Which foot? Think about how we fill a heap. What?
Yeah, you find the minimum value in the leaf nodes, no?
Nope. When we did it earlier, we just took 16. 16 was definitely not the minimum leaf node. Why did we take 16?
No. Because it was the rightmost value on our leaves?
It's the last node in the heap, basically, right? If we're filling top to bottom, left to right, it's the last node. So it's the least effort.
Gotcha.
Right? It just pops up there, and then we run the algorithm top to bottom. Easy game, right? Now, here comes...
Wait, so it's first in, first out?
Kind of. I wouldn't use those terms because it's kind of sketch. Just think of it as the last node,
right.
And the word last will make more sense in a bit. Now,
Okay.
let's go through this again. So, we have our heapify down. Beautiful. But now, let's take away this pop, right? Let's take away this heap sort. Let's move this guy into the corner. Now let's talk about... Oop, sorry, I'm on my brightness. Add. So, operations. Add. That doesn't work, whatever. Let's talk about add. So, adding to a heap. First off, I said if I want to add an item to a heap, it always goes where?
Bottom left.
Close? Oh, well, no, sorry, you're correct. Yeah, no, that's
right.
right, that's right, yeah. It's technically the bottom left. I was
Okay.
looking at this and I was like, oh, it's on there. Sorry. Confused myself there. Add value to bottom left. All right, I want to add 69. No, I want to add 1 to this heap. So I'm going to add 1 to this heap. Goes right here, right? Oh. I've added 1. Hooray.
Yeah, it goes right there. Yep.
Is this a heap?
Is this a heap? No, it
Why
is
not?
not a heap.
Why-
The 15 is greater than the 1.
15 is greater than the 1. So, our add algorithm is easy. Add value to the bottom left, fix the heap. Done. 2 steps. Just fix it. Right? Easy. Done it before. Right? Totally nothing new.
Okay.
Right?
I don't like it. Okay.
Yeah. If you're afraid, you should be. So
I am. Because this is, yeah, okay.
Right. So, we had this magical heapify down algorithm, and I told you, the reason we heapified down was what? Why did we start at the top? Let's even scroll up a bit and go look at it. Why did we start at the top? What were we doing? So keep in mind, we started here. What did we do?
Yeah. What did we do? Well, we just replaced, we just kind of iterated recursively, starting from the top to the bottom. The reason why we started from the top,
So we popped,
because it's the root, no?
right? We popped 1, right? I wanted the lowest value.
Yeah.
I said, give me the lowest value. So this
Yes.
happened. So I did this, right? I removed that 1. And
Yep.
then what did we have to do?
And then we had to replace it. We put the 16. We took the bottom rightmost number, put it up, and then we had to fix it.
Good. So, why did we start fixing from the top?
Is it because our top is supposed to be our smallest value in the heap.
Exactly. The top's where the problem is. You have to fix the cut where it is.
Yeah.
Right? If you chop your arm off and I put a band-aid on your leg, it's not going to save anybody. Your leg was fine. Your leg's still fine. Right? So, let's come back down here. So, I've just added 1 to the heap. Where's the problem?
It's not the lowest value.
It's at the lowest value. And I know exactly where it is because I just put it in there. So, now we come to our new algorithm. Heapify up with node, new node. Call it that. So, Melky, I face you with the same question I did earlier. How do you do it? You've written this algorithm the other way.
So we start with
I give you
the new
1.
node. Our new node is 1. Yeah. So do we have? So if we look at 1,
write it in English.
is one of a property like? Is one of a property called node.parent?
It does now.
So it does. Okay, so I can access that. So I'd say, if new
Actually,
node is
just to make this a little bit, this is actually just gonna make this more clear. I'm gonna also add this 7 in, just so that you have 2 children, so that you account for that. Hold on. So this is gonna be our 1, and we'll just pretend that this 7 was already here, which is fine. Just so that you're thinking in terms of the 2 children, at least.
So the easy statement would be if the new node is greater than new node dot parent. Oh wait, do I want greater? Yeah, I do want greater. So if it's greater, then we can return because we need to assume that our heap was already in order. So if our parent node is a value that's greater than new node added, then we know for sure that new node value is going to be less than the root node, assuming that the structure of our heap was already fixed to begin with, right?
Yeah. So if 1 is greater than 15, we definitely don't have to do anything because that's a min heap.
Exactly.
And the heap's fine. Nothing has broken.
Exactly.
But
Exactly. The hard part.
yeah, go ahead.
The hard part is when it's not in that case. It's when 1 is less than the parent. So if the new node is less than new node dot parent, right? Basically, what I think we should do, right? I'm trying to talk out loud. Is we swap new node with new node dot parent, and then what we would do is call heapify up with heapify up with the new node.
Be careful.
So I think we should do.
Be very careful here. Which node are you really calling it on?
Yeah. Okay. So the parameter I knew was kind of messy. It's not new node because we swapped the results, right? So we swapped new node with new node dot parent, meaning that
How about you say
new
swap
node
the
dot.
value of?
All right.
Just to make things a little clearer. Swap the value of new node to new node dot parent. Kittle, as far as we're concerned, yes. We're gonna say that they have that pointer.
But yeah, so we swap it. So thinking out loud, we swap 1 with 15. And now we have to recursively hit up, heapify up with that new value, which would be, I can still put a new node because we did swap the value, right?
We swapped the values. So now, which node has 1? Do I have the
new
lowest
node dot
one?
parent.
You got it. Is that it?
Let's see. Let me think of it out loud. So start from the beginning. If new node is greater than new parent, return, which is not. 1 is less than 15. So if new node is less than 15, so actually I'm gonna do this. I'm just gonna swap it, right? I'm just gonna follow my own algorithm here, if you don't mind, Dan.
Go ahead.
So we just swapped it, right? Now, based on my logic that I wrote here, we then call heapify node again. to start from the top, is this greater than 2? Is 1 greater than 2? No. So then if the new node, a parent that we called it with, is less than the parent, which it is, we swap the value. So then we swap 1 with 2, and 2 becomes 1. So we have 1, 2. Now my question to myself is this still a heap?
A legendary question.
1 is... hold on. 1 is less than 4 and 2. Something about where 4 and 2 kind of looks strange to me, but you know what? Maybe that's just me.
Remember the rule of a heap is that a heap is a binary tree, not a binary search tree.
Okay, so then okay, perfect. So then if it's not a binary search tree, then the rule of the left node.left being less than the value of node.data doesn't come into place here. So then with that, this to me is a valid heap.
And that it is. And that is your heapify up algorithm.
A min heap, a valid min heap. A valid min heap. That should be actually a key distinguishing factor here.
Absolutely is. Good call. And there you go. That is how you add to a heap. Now, we can go get into graphs if we want to jump to there, but what I'd like to do is blow all of your minds with how heaps actually work. Here is what is so astounding about this particular way that I've described heaps. So let's give ourselves a legendary title, Medium Data Structures, Heap Implementation. I would normally not need to talk through this, because normally with our other structures, the objects I gave you were correct. This root of the binary search tree had a data, it had a node.left, node.right, easy enough, right? And with the linked list even, all the way back up, it was as simple as, truly, you would implement it as simply data and a next node. But heap, you realized very quickly we needed more information, right? There was a parent all of a sudden, and there was still a left child and still a right child. So you would almost start to think that maybe the root of this heap, and I'll copy it down to this next page, would be data 1, left node 4, right node 2, and parent null. And you could do it that way. You could absolutely implement it that way. But there's one magical way to build a heap that makes it so much more interesting and so much more efficient that it is by far and away the way that it is built, I would say 90% of the time. Every time I've ever seen it. And that is, you can build a heap from an array. Just an array. Now I'm going to swing us way back to the top here, and let's look at our array. What does an array give us? A fixed size list of elements of the same type. That's about it. So, that's a little weird. I wouldn't say that our heap has a definite size, for sure. But what I do know is we talked about filling it left to right. So I'm going to give you an array here. 1, 4, 2, 7, 16, 7, 15. Can you tell me how I wrote that? Or why I wrote it in that order?
Yeah, I think you did. Off the top of my head, I think it's a prefix order or a postfix order.
How do you fill a heap?
Leftmost, left bottom.
And how did I write the heap?
Not left bottom.
1, 4, 2, 7, 16, 7, 15. What was that? Oh, dude!
Top left.
Thank you, totally. I appreciate that, bud. That's super kind of you. Wow, wait, that means... Oh, that's so wild. I have subscribers for 2 months now. That's, like, so new. Oh, yeah. We passed my streaming anniversary a few days ago. I didn't even think of that. That's hype. So what kind of order did I just take that in? This isn't anything that we've talked about before.
Top left?
It's really each level. So sort of. Like the words that you're saying are not incorrect, but they're not exactly correct either, right? So I print left to right, the top level, and then I print left to right, the next level, and then I print left to right, the third level. Right? Don't think of this as an algorithm. This is an array. This isn't actually a print. I shouldn't say print. This is just how I'm storing the data. Right? Where does the next value go?
Bottom left.
And what's that value?
7.
And where's 7 in our array?
It's the 4th value in the array.
It's the 4th value in the array. And so where would 16 have to be?
I would think 16 would be where 7 is right now. Like it would be on the left of 2.
Now remember, we fill the whole level, left to right. So I put in 7, it goes here. I put in 16,
Yeah.
it goes as far down and as far left as it can. But remember, every level has to be filled, right? Allow me to do this for you.
Okay.
I'm going to add 4 to this heap. Where does 4 go?
Bottom left, so it would be to the left of 1.
I'm going to add 2. Where does 2 go?
To the right of 1. You have to fill that level up.
Great. I add 7. Where does 7 go?
To the left of 4.
I'm going to add 16. Where does 16 go?
To the right of 4.
I'm going to add another 7. Where does that go?
Left of 2.
And I'm going to add a 15. Where does that go?
To the last remaining spot on that level, which is to the right of 2.
No, that's so interesting. That we're able to just write this array, and that even though we're looking at a tree, this tree has order to it. There's a left to right here. There's a progression here, right? Thank you so much, Nir. Really appreciate it. So, here's the question. And this is going to get big brain. So I'm just going to kind of show you how to do this one. So let's write out our indices here. Index. Zero, 1, 2, 3, 4, 5, 6. Right, so there's all your indices. What is 1's right child?
2.
What is 4's right child?
16.
And what is 2's right child?
15.
Great. Now, let's do another one of these. What is the index of 1 and then the index of 2?
0 and 2.
What's the index of 4 and then the index of the 16?
1 and 4.
What's the index of 2 and the index of 15?
2 and 6. Well, there's a pattern there.
There's almost a pattern. Something's showing up here. Something very important is showing up here. Now, if I asked you what the index of 22 was,
It would be... It would be, that's tricky because there's 2. It would be 3 and 7. No, wait, it would be 3 and 8.
3 and 8.
The only reason why I knew that was because the pattern was established. I didn't even have to think about it. Only part I was confused because there's 2 7s, but I kind of was just like, okay, wait, hold on.
Yeah, sorry about that. We can just change this to like a
All good.
10.
So yeah, so 3, 8. What?
Something's coming. Something's showing up here. Patterns are hard. More data helps. 16's right child.
Let's see. Okay, I'm not gonna think about it. I'm just gonna say it's 4 and 10.
Super interesting. So you'd be right. How's that work?
I have no idea.
Let's look at how far we had to go for each one.
Okay.
What's the distance between each of these? What's 2 minus 0? Right, so I'm gonna put
2.
distance here. Oof. Please. Help. Say dist, right? 0 minus 2. Or 2 minus 0. 2. 4 minus 1?
Yep. 3.
6 minus 2.
4.
8 minus 3.
5, 6.
Weird. Super weird.
Bro, what are you doing? Why do you keep...
Super
That-
weird.
Actually, did I ever tell you I hate you?
Yeah, you should.
Because I do.
Now, if I asked you for a formula to go from index 0 to 2, from 1 to 4, from 2 to 6, from 3 to 8, and from 4 to 10, could you give me this formula? I'll tell you this much. This distance actually won't help you too much. This might take a
Wait,
while.
you're
Do
telling
you
me-
want me to give you the formula?
Wait. No, hold on. Let me try to understand the question. You want me to give the formula to go from index 0 to index 2?
The formula to go from 0 to 2, to go from 1 to 4, that will go from like, so call it like A to B, right? So how do you make a formula that is 0 to 2, that is 1 to 4, that is 2 to 6, that is 3 to 8, and that is 4 to 10? All of these follow one formula. What is that formula?
It would just be the distance between B minus A.
Right, but you don't have distance, right? You need to figure it out. I don't know. We wrote down index 2, but I need to be able to come up with the number 2 from 0. So how do I get from 0 to 2? There's only one way to get there.
Add 2. But we don't know what 2 is what you're saying, right?
Well, let's just keep this here, right? Now, how do I get from 1 to 4?
Alright.
I have to at least do the same
Add 3.
thing. Right? I have to, so we're coming up with a formula, right? So I have to do something, and then I still have to add 2 at the end. Do you understand where I'm getting at? We're writing a formula. So basically we're saying something about A and something about A equals B. Right? And we've established
Right.
in some way, shape, or form there's a plus 2 in here. So I have 1. I have to do something with 1 and then add 2 to get to 4.
Can you add itself? Can you do 1 plus itself plus 2?
So double it.
Double it? Because that would hold true for all the other instances as well.
Does it? 2 times 1 plus 2. Does that work?
Yep.
2 times 2 plus 2. Does that work?
Valid.
Right.
Yep.
2 plus 2. This results in 4 plus 2. This results in 6 plus 2. And this results in 8 plus 2. Does that work every time?
Seems so. In our example cases, it does.
So, I told you earlier that your right is going to be a pointer to a node. But really, your right is going to be heap at 2 times index plus 2.
Jesus.
We don't need a pointer.
Jesus.
We don't need an object.
We just need the index.
We just need the index. Now, same question. Can you do the same thing for left? Left and right child. There's only one thing different between them. What's the difference between the index of 33 and 22?
1. It's one value.
And what's the difference between the index of
Would
40,
it be-
20, and 69?
One value. So would it be +1 instead of +2?
Boom.
Bro, what?
Now, come on. Big brain time. Let's give ourselves another kind of table here. Let's reverse it. Right? So we know 1 is... hold on. 2, child of 1. We got 16 is a child of 4. We got 15 is a child of 2. I think. Yeah. We got 22 is a child of 7. We got 69
No,
is a child of 16. Right?
Yeah, I think 22 is a child of 10.
So, 2 is a child of 1. 16 is a child of 4. Let's do this thing again. Actually, we have all these numbers already, so I'm going to just type them in reverse.
6, 2, 8, 3, 10, 4.
Yeah, I did one backwards. Now, I'm going to add one set of indices. These are all, I want to say these are all right children, probably. So, what if I added all the left children? What did we say earlier is different about the left children?
It would just be 1, 0, 3, 1, 5, 2, 7, 3, 9, 4.
1, 0. Well, okay, so if 4 is the... So it's 3, 1. Because it's 1 less. 5, 2.
Yeah.
7, 3. And I'm going to move this in a sec. 9, 4. Look at that whole list. What is that? Oh, cool! Larry, New York is rating with a party of 11. Thanks so much, Larry. Good to meet you, bud. Hey, everybody, how you doing? We're talking through heaps and graphs. We're just about to finish up the biggest mind-blowing part of heaps as arrays. Good to meet y'all. All right, so looking at these indices, is there a pattern? We were just doing algorithms online. Let's go, science and tech, fam. We're doing it. Can you give me?
Is there a pattern?
Is there a pattern? Here's the hard part. 7 and 8 both have to go to 3. 5 and 6 both have to go to 2. 3 and 4 both have to go to 1. I will remind you of a few things that exist. Floor is a concept if you want to remove a decimal. Ceiling is a concept if you want to round up. Can you come up with a formula here? Let's just take one of these. Can you make 3 and 4 go to 1?
Well, yeah, I'd just subtract, 3 from 4.
But you only have one of these. You have to be able to make 3 go to 1 and 4 go to 1 with the same formula.
Okay, yeah, I think I got it.
What do you got?
Divide by 2 minus 1.
3 divided by 2 minus 1 equals 1.5 minus 1 equals 0.5. 4 divided by 2 minus 1 equals 2 minus 1 equals 1. So it worked for 4, didn't work for 3. What do we need to do?
Oh, this floor rounds down? Like, if you have 0.5 would be considered rounding down?
Floor will chop off a decimal. Ceiling will toss it to the sky.
Okay. 4 minus 1 divided by 2, and 3 minus 1 divided by 2.
4 minus 1 divided by 2 gets you another 1.5.
Floor, which would be 1, right?
Are you flooring this?
Yeah.
Okay, you want to floor this.
Yeah.
Then we'll floor 3 minus 1 divided by 2, which just gives us 1 here.
1.
And with the floor, that also gives us 1. Boom. barely in D4, you guys have both. So just very quickly to call this out, what Barely and D4 have called out. So D4 suggested this, and what Barely described was this but ceiling. So that would have gotten you 1.5 and 2, and then you would have ceiling that. And so that would have gone to 2, 2, and then subtract 1. So you can do either. Oh yeah, the floor formula slightly cut out. Sorry about that. Running out of whiteboard space even online. But this works. So, writing that as a formula.
Okay, so our index.
Put this over here. Parent index from child. P equals floor. C. Here, we'll just use the actual words. Parent equals floor of child minus 1 divided by 2. Here's the thing about parent. Who's searching for their parent, right? Who am I when I'm asking who my parent is? I have to be a child.
You'd have to be a new node added. Okay.
Right, so sorry.
Can't you be a new node added in as well?
Yeah, so like here's the thing, right? When I say like my right child is 2 times index, that's my index. And so when I say the parent is the floor of the child index minus 1, well, I'm the child. It's my parent. So this is just floor of my index.
Ah.
Right? And just like that, and this is also, you know, heap of. Make me make the text slightly smaller. Just like that, without a single node, without a single object, we built an entire heap out of just math and this array. And that's it. That's all it takes. So although I gave you earlier this concept of this left and right for binary search trees and this version of the heap that was effectively the same thing for this binary tree, we don't even need it. You can do it all just using an array so efficiently, because if we also know what size the array is going to be, like if we know how many items we expect in the heap, this is a huge win. Now, there's one takeaway. Same thing of an array versus a linked list, right? What's the benefit or drawback of doing this? It's the same question as why would I use an array versus a list?
Is array set, like would it be because an array is already set size?
Yeah, and so what benefit do you get from that? Remember back to our literal like second slide. Why is it good for an array to be a set size? What benefit do we get from that?
I'm going to second slide, but I think does it have something to do with the speed or size of it, like how little space we need to consume?
Right. Thank you for the follow, Kappa. I really appreciate it. Oh, Ravens, I might have missed yours earlier. Thank you, Ravens. I appreciate it. So, simply enough, right? With this array, access, instant, right? No following pointers, no anything. I know exactly where to jump into the array. So all of my access is way, way, way quicker, right? But I have to know a specific size. All the same, there's way less overhead because I'm not actually storing all these pointers, all this other data. I'm not storing children, none of that. Just one array of straight integers in this case. That's it, right? Thank you all so much for hanging out. Melky, again, thank you for coming. 1 week from now, we will do it again. Come by and learn graphs. Join Discord to learn more in between. And just come by for startup stuff whenever, or check out Melky's stuff for any amount of bot building, machine learning mayhem. Thank you all for coming. Everybody have an awesome night. Cheers.